Hi everyone, this is Mrs. Bertrand, and this lesson is called The Mole. And you might be thinking, what does this have to do with chemistry? Aren't moles furry creatures that burrow under the earth? Or maybe it's this fabulous beauty mark right here? Well, in fact, the mole is used in chemistry, but not this way. The mole is actually just a quantity of something. So it's a word that means a number. So just like a dozen means 12 and a pair means 2, a mole means 6.02 times 10 to the 23rd particles. So there's an experiment that was done about this, and they figured out that this is the amount of a mole of any substance on Earth. So if I had a mole of people, I would have 6.02 times 10 to the 23 people. Particles in chemistry could mean atoms, if I'm talking about things like copper and magnesium, or they might be molecules if I'm talking about water or magnesium oxide, something that more than one element is put together. And a mole is a really big amount. And the reason why is because when I'm talking about atoms and molecules, I need a lot of them before I can even see them because they're so tiny. So again, 1 mole represents this 6.02 times 10 to the 23rd particles, and that is a consistent, constant number. Every time you hear the mole, that's the number that we have in mind. The mole is also known as Avogadro's number because Avogadro actually came up with this theory and this number. Unfortunately, he passed away before he was accredited with it, but they named it after him, so at least he got there in the end. So why do we use the moles? Again, it's because when we're talking about things like atoms and molecules and compounds, they're so small, it takes a lot of them before we can even see them. So we actually count in terms of how many moles of something we have versus how many atoms we have. We can do both, but we can't actually count single atoms out because we wouldn't be able to see them in the first place. And it would take us way too long to be able to count enough until we could see them. So again, in chemistry, we use this thing called the mole. When we're doing mole work, we often will convert between different types of things. So we're going to start by looking at converting between moles and particles. And the relationship we learned is that 1 mole equals 6.02 times 10 to the 23rd particles. So this relationship, and any time two things equal one another, we can actually use it as something called a conversion factor. The two conversion factors here are listed below, and you can see they've got both parts of this relationship, but I've used them in different ways. So on the left-hand side, I have moles on the top, particles on the bottom, and on the right-hand side, I have particles on the top and moles on the bottom. This is going to help me work out the math as I go from one type of thing to another, as you're going to see. So let's jump into this first question. I want to know how many atoms are in 2.45 moles of copper. So I'm going to start the question the same way every time, and I'm going to recommend you do the same thing. Start with, what am I looking for? So as you read the question, what am I looking for? I'm looking for atoms. So I'm going to start the problem by writing down atoms equals. Then I'm going to put in what I know. I have 2.45 moles. I'm going to write that next, 2.45 moles. Now it's time for that conversion factor. I'm going to write it on this sheet down here at the bottom here. 1 mole equals 6.02 times 10 to the 23rd particles. And let's see how we would use it here. Now the first thing I'm going to do is I'm going to decide what word I should put in place of particles. And in this case, I'm going to use the word atom because I'm counting copper, which are atoms. So I'm going to do that change first. The next thing I'm going to do is I'm going to use this relationship, and I'm going to now multiply by it as the fraction, the conversion factor. And what my job is to decide what part of this relationship, moles or particles, or moles or atoms in this case, goes on the top of my conversion factor and which one goes on the bottom. The whole way to solve this is to look at the units. So the units are key. What units do I want to end up with? What units do I need to get rid of? So here's the relationship. I want to put 6.02 times 10 to the 23rd atoms on top, and I want to put the 1 mole of this puzzle on the bottom. Here's why. I want to be able to get rid of the unit mole here. And if moles or any unit is on the same on the top and the bottom, I get to cancel it out. That leaves me with atoms on top, which is precisely what I'm supposed to be getting. So this now tells me the math is good and I can proceed. So when I'm using my calculator here, I've put it down here in the bottom, but here's how you would type it in. 2.45 times 6.02 exponent button, not times 10, exponent button, it does times 10 for you, and then your exponent, in this case 23. So again, you're going to type in 2.45 times 6.02 exponent button 23. And this is what you should get, 1.47 times 10 to the 24 atoms. Now, you can see the number's probably not an exact match to your calculator because I'm making sure I do a final number with the correct significant digits and units. And when I look at the only number given to me in the problem, there are 3 significant digits here, which means at the end, I also need to keep 3 significant digits. So a lot went on in that question, really important. We're going to try one more together here, and let's see if you can get it. All right, so for this second question, it says, how many moles are in 3.87 times 10 to the 25 molecules of ferric chloride? So again, start the process. My first part of the question asks me, or the first thing I want to do is, what am I looking for? So I'm looking for moles, so set it up. M-O-L is the short form for mole. Not saving us a lot, but you can use the whole word if you want to. Now we're going to put our equals. Now we're going to put the thing we do know, 3.87 times 10 to the 25 molecules. Always keep the unit. That's going to help us when we get to our conversion factor. Now we're going to consider our conversion factor. Let's write it down here at the bottom again. 1 mole equals 6.02 times 10 to the 23rd particles. Good old Avogadro's number. Sorry, that's my computer. And again, the first thing I want to do is make a change for particles. For particles, get rid of that. And we're going to use the appropriate word for this problem, which is in this case molecules, since it's ferric chloride, more than one element. And now we've got to decide how to use this relationship as a conversion factor to get rid of the units we don't want, keep the units we do want. In this case, we're going to put mole on top, 1 mole, and Avogadro's number on the bottom. Hopefully, you're starting to make sense of this at this point, because we need to get rid of molecules. And again, any unit that's the same on the top and the bottom, we can get rid of it. And I want to end up with moles on top here, just as I set up the problem, so that does this for me. So we can actually let this drive the math, if you will, so to speak. So let's do the math on this one. Again, I'm going to explain how to put this into your calculator. We're going to type in 3.87 exponent button 25 divided by 6.02 exponent button 23. So notice at the top it says 3.87 times 10 to the 25 times 1 and then divided by 6.02. Anything times 1 is not going to change the number, so I go straight into the division. So again, 3.87 exponent button 25 divided by 6.02 exponent button 23. You should be able to get 0.3 moles. Again, this is not what the calculator shows. However, what I'm doing is I'm being mindful of those significant digits again. That is my job. So I've got 3 significant digits given in the problem. I need to show 3 significant digits in my final answer as well. It's okay to show what the calculator spits out at you here and then rewrite it as a final answer. That's totally fine as well. So long as you get to that final answer with the correct significant digits and units, that's what I'm going to be looking for. All right, I'm going to do another conversion now. This time I want to convert atoms to particles. So we did moles to particles, now we're going to do atoms to particles. So the first part of the question says, how many atoms are in 1 molecule of H2O, water? If we count atoms in 1 water molecule, there are 2 H's and 1 O every time. This looks like 10, but this is actually an O here. That's an oxygen. So in total, there are 3 atoms. So anytime, and I mentioned this before, anytime you have 2 things that are equal to one another, you've now created a conversion factor. So this is exactly what we're going to do for this second type of conversion factor. You're going to consider 1 molecule of a substance and figure out how many atoms it has, and now we can go back and forth between molecules and atoms. So again, here's our generic conversion factor. 1 molecule equals number of atoms. And this one isn't consistent like the last one where we had that Avogadro's number, because depending on the molecule, the number of atoms will change. So I'll have to consider every new molecule that I'm given, and that will change the number of atoms. Again, once I have my relationship, then I can use it as a conversion factor or a fraction to get rid of the units I don't want and keep the units that I do want. So I can have molecules on top of atoms or atoms on top of molecules. Let's try a problem together. So this says, how many atoms are in 0.65 moles of NaHCO3, sodium bicarbonate? So the first thing I need to do is actually come up with my relationship between atoms in a molecule. So if I have a count, I have 1 sodium, 1 hydrogen, 1 carbon, and 3 oxygens for a total of 6 atoms. So in this particular problem, I've got a relationship that I just made, 1 molecule equals 6 atoms. But in this question, I actually have to use my first conversion factor as well, because I also have moles. And moles doesn't show up until I go back to that first conversion factor. So I now have 2 conversion factors that I'm going to need to use this time. Let's see if we can figure out how to work this out. So again, I've just brought those conversion factors with me to this slide along with the question. And I'm going to set it up exactly the same way as I did the last time. So what am I looking for? Atoms. So atoms equals. And then what do I have? 0.65 moles. Now it's time to go to our conversion factors. Now this is a little bit trickier because I have 2 choices here. And I don't have one relationship between atoms and moles in this context within a compound. And so I actually have 2 conversion factors that I have to use. And the first thing I have to do is I have to get rid of moles, which means the only conversion factor that has moles in it is this one here. I have to use this conversion factor first, the first one that we learned. So here's what I have to do. I need to get rid of moles. I'm going to put moles on the bottom. Avogadro's number is going on top. Whoopsies. Let's get the right lingo here. Since I'm talking about sodium bicarbonate, that's a molecule since there's more than one atom there, or more than one element. So that allows me to get rid of moles. But you'll notice that I'm stuck with molecules and I need to go to atoms, which means I'm going to now employ the second conversion factor to get me to the end point. So again, let's multiply again, and let's look at the 1 molecule equals 6 atoms relationship to see who goes on top, who goes on the bottom. Units drive the process. So I have molecules left right now from that last step. I want to get rid of those molecules. So let's put molecules on the bottom. 1 molecule equals to 6 atoms. That allows me to get rid of molecules now, leaving me with atoms, which is precisely what I want. So now that I've set that up, I can do the math. So in our calculator, 0.65 times 6.02 exponent by 23 times 6. Our final answer should be 2.3 times 10 to the 24 atoms. Again, your calculator will spit out more numbers at you, but I'm limited by the significant digits given. I've got 2 significant digits here. That means I only get to keep 2 significant digits in the end. And again, it's okay to write down everything your calculator spits out at you, but then you have to do a final answer to make sure significant digits are in line. And of course, it wouldn't be a good lesson unless you had time to practice. So it's practice time, everyone. Huzzah!